Today we will be discussing about a case study from Thyssen Steel Europe on the influence of deteriorated coke properties on blast furnace performance. This study focused on a large-scale experiment conducted at BF2, one of Europe's major furnaces. As you all see, the result provide critical insight into necessity of high quality coke for stable and economical blast furnace operation. The motivation for this study is a pressing issue in our industry. High quality coking coal is becoming scarcer and more expensive. Modern blast furnace aiming for low cost inject large amount of substitute agent like coal, which places even greater demand on the remaining coke. This coke is not just fuel, it's a critical structural material that ensure gas can flow, support the weight of the burden, and allows hot metal and slag to drain in the furnace hearth. To understand the risk, Thyssen conducted a bold experiment in 2011. For nearly 8 weeks, they internationally produced quality reduced coke at their coking plant by increasing the share of petroleum coke in coal blend. This inferior coke was then immediately charged into the large scale blast furnace. Number two, the study compares furnace performance during this trial period with a preceding reference period to precisely measure the impact of poor quality coke. The change in the coal blend had a clear and significant effect on the coke's property. As you can see in any literatures, the average coke size after tumbling decrease, the coke strength measure as I40 dropped from a respective average of 54.6 down to a minimum of 45.2. Perhaps most critically, the hot strength or CSR value plummeted from an average of 68.9% to just 59.1%, hitting a low of 50.8%. This value is vital for the coke performance in the lower high temperature part of the furnace. Interestingly, while the ash content went down, the sulfur content increased due to petroleum coke. The data is unequivocal. The coke quality was substantially degraded during the trial period. The furnace's reaction was swift, especially in the upper section. The top gas utilization, a key measure of efficiency, dropped by over 1% on average, meaning the gas was doing less work. Top gas temperature rose significantly across the entire furnace radius up to 200 degrees Celsius in some areas. This indicates a less stable and less efficient process. Furthermore, the generation of dust and sludge, which must be managed, nearly doubled from about 13 to almost 18 kg per ton hot metal. We also saw a sharp increase in cooling losses in the lower shaft, pointing to higher thermal load on the furnace wall, which is a major concern for equipment integrity. This instability was not isolated, it cascaded through the entire operation. Blast condition become progressively worse, forcing a reduction in blast volume and leading directly to production loss. The furnace experienced more frequent checking, slips and channeling, all sign of poor gas permeability and an unstable burden column. The pressure drop across the furnace frequently hit critical level, indicating the process was on the verge of collapse. The physical toll was also severe. Tuer failures, which are costly and disruptive, increased by 2.5 times the normal rate, likely due to scaffold formation in the Bosch area. Finally, the process became chemically unstable with wild fluctuation in hot metal and slag quality. The furnace produced over 25,000 tons of non-sellable high viscosity slag during this period. The most dramatic physical evidence came from a lower furnace. Core drilling at the tier level was performed to measure the raceway, the cavity where combustion occurred. The results were, as the report says, extremely disappointing. The raceway length was found to be just 0.44 meters during the trial. For comparison, under normal condition, it measured 1.06 meter, more than double the length. These drastically shortened, these drastically shortened, these drastically shortened, uh, shortened raceway, along with an increase in fine coke particle in the dead man and evidence of scaffold formation, which proves that the poor quality coke was breaking down and could not maintain the essential structure and gas flow in the heart of furnace. So, how quickly did this problem appear? A cross correlation analysis revealed two different timelines. That immediate impact within 0 to 2 days was linked to coke size and cold strength. As the cold strength dropped, the pressure drop in furnace immediately increased and hot metal production quickly shifted from a surplus to a loss. However, the hot strength CSR had a delayed impact. It took about 12 days for poor CSR value to begin negatively affecting production. This delay is because it takes time for inferior coke to work its way down and replace the existing high quality coke in the furnace dead man. This shows that while cold strength is critical for the immediate stability, hot strength is absolutely essential for long term health and performance of the furnace health. In conclusion, this experiment provided definitive proof that a large scale blast furnace simply cannot be operated in a controlled or economical manner with a poor quality coke. The use of deteriorated coke causes severe system wide problems from top of the furnace to hearth. Cold strength I-40 immediately impact gas flow and production, while hot strength is fundamental to long-term structural integrity of hearth, which is crucial for the flow of gas and liquid product. The central importance of CSR value cannot be overstated. This study makes it clear that investing in high quality coke is not a luxury but a requirement of reliable, efficient, and safe blast furnace operation.